So the lecture segment objectives here in this, this first segment, I'm going to talk about incorporating the ideal gas law into stoichiometry and using Dalton's law of partial pressure to relate partial pressures to gas compositions. Let's dive in. So a gas stoichiometry example. So a lot of the stoichiometry comes down to how can we figure out how many moles of a substance there are. Once we know the number of moles, then we can use the chemical equation to relate that. So the ideal gas law allows us to measure numbers of molecules by the volume or the pressure of the gas. If we know the volume of the container, then the pressure is enough to tell us, we know the temperature, the pressure is enough to tell us how many moles. Or if we know what the pressure is, then the volume of the gas will tell us that. So the reaction used in the deployment of automobile airbags is the high temperature decomposition of sodium azide, sodium N3, to produce N2 gas. So how many liters of N2 at 1.15 atmospheres and 3.0 C are produced by the decomposition of 45 grams of sodium azide? So what do we need to do? So first we need to figure out how many moles of N2 are going to be produced. So let's start. So we have the equation here, and we'll need to look up or calculate the molecular mass of sodium azide. It ends up being, yep, that's good. It ends up being, oh no, slightly other, that's good, okay. 65.02 grams per mole. So 45 grams of sodium azide, 65.02 grams per 1 mole. That would give us 0.692 moles. And actually, we don't need to calculate it. That's fine. 692 moles of sodium azide, Na3, and then we know that 2 moles of sodium azide, NaN3, react to produce 3 moles of N2. So we get out 1.038 moles of N2. All right, so now that we know the number of moles of N2, you can probably guess approximately how many liters is going to be produced right now, but we'll go through the calculation. So we start with PV equals nRT. And so the volume is going to be nRT over P. So the number of moles, we know that 1.0038 moles are. So we're looking for a volume in liters and the pressures in atmospheres. So we should use the gas constant in liter atmospheres per mole Kelvin. So 0.08206 liter atmospheres per mole Kelvin. And then we need the temperature. Notice it's given in C, so we need to add 273.15 to get 303 Kelvin, and we only have 3 significant digits. We'll leave it at 303 Kelvin. The pressure is 1.15 atmospheres. And because there's so many units at play in PV equals nRT, I like making sure I write out all the units explicitly and then canceling them. So atmospheres cancel, Kelvins cancel, moles cancel, and we are left indeed just with liters, and we get 22.45 liters. We're close to standard temperature and pressure, and we have about a mole, so we'd expect to get about the molar volume of an ideal gas. So that's a lot of gas that's produced from just 45 grams, not much at all of a molecule. Okay, so that is how we bring stoichiometry, ideal gas law into stoichiometry. It gives us another way to measure number of things.